So my name is Guillaume Prats. I'm one of the faculty in the Department of Radiation Oncology, and I'll be teaching today the course on tomographic image reconstruction. So just as I was saying, a few words about kind of how this course is going to go in this lecture. So there's a document camera, which is my phone. It's you can actually pin it to your screen so that it will show full screen on your and you can follow what I'm writing instead of having the full screen being the camera, right? If you have any problem about technology, you can just maybe either send a chat to the TA, who's Wes Foster, or Craig. Craig is the course instructor. So other couple of things I wanted to mention. So I sent a video earlier on. I think it was sent on Monday, and I hope everybody was able to watch the video. So this is kind of a review maybe for some of you, but for some of other people, it may have been new material. And hopefully this was helpful in understanding how images are represented, especially when we talk about images in the frequency domain. And we're going to be relying heavily today on this concept of frequency domain. And so I really hope that this was something that came out and was clear to most of you. The other thing I wanted to mention, and I'm just going to briefly share my screen here. So, sorry, just try that again, share screen. All right. Okay, so there's lecture notes that are posted online. So this is, if you want to kind of review what we talk about today and on Monday, you can actually go through those lecture notes. They will kind of explain. So this is about the frequency domain right here. There's a short section image quality that you can read, but it's not really. It's kind of optional because the course is a bit shorter this year. And then I think the important part is going to be the section about starting from section 2 on tomographic image reconstruction and acquisition. So this is, you may want to use those notes to review the course material later. So you have the notes here. And so, yeah, feel free, of course, to always email me if you have any question about the lecture or the lecture notes. So my email is on the screen here on the document camera, if you can see it. Okay, so with this, we'll get started officially. So you want to put your screen on the document camera right now, because I'm going to basically go through the course mainly using the document camera. All right. So just want to introduce the concept of tomographic image reconstruction to you. And first of all, we're going to talk about tomography, right? And this is a word you may not have heard before because it's not a very common word. And so tomography basically comes from two Greek words, tomo, which means to cut, and then graph, like graphos, which mean to draw. Okay, so when people invented tomography, basically they went to Greek words and they came up with that word of tomography, which means we're going to draw cross sections of something, right? And the basic idea is if you were wanting to look at the inside of some object. So think about maybe like an apple, and you want to know what's inside this apple. Is it the apple rotten or is it fresh? What you could do is you could slice the apple into thin sections with a knife, and you could see if there's any spoilage of the apple, and you could take pictures of those slices, and if you had many pictures of every slice of the apple, you could kind of create a three-dimensional model of your apple, right? And so in medicine, we often want to know what's going on inside the patient, whether the patient may have a tumor in his lung or her lungs, or in the liver, and we need to have access to tomographic information to know what's going on with the patient. But because we can't really cut the patient into slices, we have to use different type of approaches to see what's going on inside the patient, and that's where tomography is going to come in. Okay. So the definition of tomography is that it's the formation of cross-sectional images from external non-invasive measurements. So the idea is we're going to use some kind of instrument, whether it is ultrasound, X-ray, gamma rays, or magnetic fields, and we're going to require external non-invasive measurements of the patient and try to understand what's going on inside the patient, right? Trying to see if there's a biological process going on or some anatomical changes that have taken place and that we can measure using this approach of tomography. So, you know, earlier in the course, you've learned about radionuclide imaging. And so this is the example we're going to follow through this lecture. Doesn't mean that this doesn't apply to other type of tomographic imaging, but just to make it more concrete, we're going to talk about mainly about radionuclide imaging. So this is tomographic radionuclide. And so in radionuclide imaging, we're using a radio tracer. So if you know, patient comes to the hospital and has, you know, maybe pain in the stomach, all right? Something's going on in the stomach. I want to know if, you know, maybe there's something going on, and we can, let's assume we have a tracer we can inject that's gonna maybe tell us about what's going on, the source of the pain. And so the idea is with radionuclide imaging, we take the tracer in a little syringe here, we'll inject it into the patient. The tracer will get into the blood flow. The blood goes everywhere in your body, so the tracer is really going to perfuse all the organs in the body. And it's going to be retained wherever there's that biological process of interest that we're interested in. So maybe if there's a tumor, the tracer is going to bind specifically to tumor cells. And so now, you know, the patient has essentially, the tracer is distributed in the body, and maybe it has accumulated in some region of the stomach where something wrong's going on. So what we want to do as a doctor is want to take cross-section images of the patient. So the idea of what's a cross-section, we're going to essentially, it's like taking a virtual slice of the patient. And this is going to give us an image of the distribution of the tracer in that region, right? And so the video talks about what's an image. I think if you've watched the video, you'll know that images are basically arrays of pixels or voxels if it's a 3D image. And the goal of tomographic radionuclide imaging is to acquire those images in 3D. So, you know, before tomographic imaging existed, there was a simpler method, which was, the idea was to take a biological specimen. So let's say this was a tumor that's maybe taken out of a patient or an animal. And the tumor has been labeled with a radio tracer, and the idea was to cut those tumors with a very thin razor blade, and then putting the thin tumor sections onto a piece of film. So this would be a piece of film here, but not photographic film, but radiographic film. So it's a film that's sensitive to gamma rays. And by waiting a few hours or a few days after that, we could take the film out and basically get a picture of how the tracer is distributed into that tissue slice. Okay, so this is kind of an invasive type of radionuclide imaging. So this is ex vivo. It's not inside so ex vivo meaning outside the body. So it's an invasive approach. But what we're going to do with the scanners that we have is that we can actually do that non-invasively inside the body instead of using a knife to cut the tumor, we're going to use mathematical tools, right? So for tomography, you know, basically mathematics are going to play a big role. So a few words about, you know, so why learn reconstruction? And I think there's a couple reasons why. One is that there's many methods available. So it's important to know which method to use for you know, different applications. And then for each method, there's many parameters also, right? So having an idea of what parameters to use, what the parameters mean, understanding image quality. So that's another aspect, is the idea of understand image quality and obtain the best image quality possible. So this is sort of somebody who may be a user of this type of scan. So either somebody wants to go in medicine and want to understand imaging, or somebody who wants to use that as a research tool. And I think, I mean, another reason is, of course, is I think reconstruction is kind of a fun thing, and you use math in a kind of an interesting way. So I think it's sort of interesting in itself. And the main concept that I would like you to remember from the lectures today and on Mondays basically are this idea of tomography, which we've talked about. So this is an important concept. The idea of image, what are images? You know, in 3D, in the frequency domain. So just having this idea how we represent images and what they mean. And then we'll be talking about something called a sinogram. That's also an important concept that you may not have come across before. And then we're going to talk about two types of methods, analytical versus iterative method. And so this idea that there's multiple methods to do reconstruction, I think is an important concept of the course. So this is sort of a summary of what we'll be talking about over the next two lectures. All right, and I just want to go briefly. So, we talked about images during the video. So, images is a stack. So a 3D image is a stack of 2D images, and each image is a 2D array of pixels. And the important thing we talked about is this idea that we can have some kind of image. We'll talk in 2D just to make things simpler, but everything kind of extends to 3D. But if we have an image like this, which maybe represents a tracer distribution, we've talked about the fact that, so this would be X and Y. These are kind of spatial coordinates. We talk about the fact that we can apply something called a Fourier transform. So, which in this case is in 2D. And we can get spectral information for this image, okay? So that this is taking the image into a different space. And in that case, at the center of the spectrum, we have our, the DC component, which is the low frequency, the zero frequency, and then there's going to be, different types of, so higher and higher frequencies. So if this is the zero frequency right there, and as we go here, we go towards higher frequencies, and we're going to talk about spatial frequencies here, Kx, which is the spatial frequencies in the horizontal direction, and then Ky, which is spatial frequency in the vertical direction. And the idea is, a point that's here as a high spatial frequency in the horizontal direction, but has no vertical frequencies, and vice versa. Okay. By the way, if you need to, if you have any question to ask, you feel free to unmute yourself, and you can stop me at any time. There's no, this is, hopefully this can be interactive. I know it's not straightforward when it's on Zoom, but I really want to make sure that, you don't feel afraid to interrupt me anytime. Just one last thing I wanted to show as a review here is, so this concept of, so hopefully you can see my screen here. So this concept of frequency distribution, frequency domain data. And so this is just to make sure that everybody understands. So this is from, I think, an exam in previous years. But this is the idea. So this problem here, what was asked about, so was to find the spatial distribution of the image that matches the frequency distribution, right? So how would you solve a problem like that? Does anyone wants to try to answer this question? I'm going to ask for if someone wants to try. So this is the frequency domain information here. You have the zero frequency here, the DC term is in the middle, and this, this frequency information in those two bands here. Anybody wants to give it a try?
Would it be like horizontal stripes?
Yeah, that's right. So I don't know who spoke, but the answer was right. So because, in that case, we have vertical frequency information, right? There's the signal is essentially focused in those 2 points of the spectrum. So it's a pure frequency signal. So it means it's a pure sine wave type signal. And because it essentially is along that axis here, so it's going to be, so the signal, I'm going to try to annotate that just to make it clear. So if I can, yeah, all right. So basically it's going to be a pattern of vertical stripes like this, right? And the spacing of the stripes is going to depend on the actual frequency that's in the spectrum. Actually, here I already gave the solution. I realized. So this is the other problem. So if we have a spatial image like this, if we take the Fourier transform, in that case, the frequency information is going to be kind of rotated compared to this one. So it's going to be rotated by about 45 degrees. And the spectrum is always symmetrical. Something to remember, if your signal is real, then your spectrum is symmetrical. So it means you can rotate it 180 degrees, and basically it's the same spectrum. if there's the stripes are more closely spaced, then that means essentially there's more cycles per centimeter, so it means higher frequency. Okay, so that just was kind of a brief review on that concept in case some of you missed the video. Any question on that? All right. Okay, so if no question, I will just move on. And then the next, so the next topic is going to be just a brief review of PET and SPECT. And we're going to introduce the idea of sinogram in this section. So first, let's start with SPECT. So SPECT is achieved using a gamma camera, as you learned in previous lectures. So if this is a kind of a 2D cross section through the patient, right? This is maybe the region of uptake, and we're going to call these coordinate X and Y here. So the gamma camera is going to be placed around the patient, and it's going to acquire projective information from the patient. So the most basic camera is a type of radiation detector that's pixelated, that provides sort of 2D information, but here we're looking at a sort of a cross-section, so we're only seeing things in 1D, right? So this is the camera kind of continues out of the plane, but this is just looking at a cross-section of the whole setup. So the gamma rays are present in here, so they they decay kind of random direction. Some gamma ray may be decaying and this way, but because of the collimator, so what I drew here is a collimator. So this is a kind of something made out of lead that doesn't let the gamma ray go through unless they're coming perpendicular to the gamma camera. So this gamma ray is going to be blocked by the collimator. And then this gamma ray here is going to go and it's going to squeeze through those holes, and it's going to basically be recorded by the gamma camera. And if we acquire data for a long time, we can make a map of all the number of counts that are being recorded. So this is the area of the patient where there's the most radioactivity. So there's going to be the most counts coming out of that tumor here. And there's going to be relatively fewer counts coming from outside. So the gamma camera we're going to use, has its own coordinate system, which is going to be, we're going to call it R. And we're also going to talk about the angle of the gamma camera as theta. And this is just going to be called theta equals 0. So that's our reference position for the gamma camera. And then we're measuring those projection data. And so around here, there's basically few projection data. And then here there's higher counts because of the tumor that's present here. So this is essentially a graph showing the number of counts recorded for different points along the camera, right? So at this point here, that's where we're recording the most counts because that's like the center of the tumor, right? And this is the projection of the whole 2D image into a 1D projection, right? So we're going from a 2D image here to a 1D projection, okay? So of course, if I only have one projection view, there's not enough information here to recreate a two-dimensional image. It's just impossible to go from a 1D projection to a two-dimensional image. But what we're going to do is the camera is going to be rotating. So we take the camera and rotate it around. And so we can, for example, look at like a 90-degree projection of the same patient. And so again, now the gamma rays are going to come at that. So gamma rays are made in all directions, right? So they're kind of coming out of random directions. And now, so R is like this. Theta is 90 degree. And then the projection is going to look something like, like something like this, perhaps. Okay? So we projected the image and we get a different image. And so, because we can acquire as many angles as we want, we can essentially organize this projection data. So the projections, we can organize them as a 2D structure, right? Which is going to be organized as a function. So we're going to call it S, and we're going to organize it as S of R and theta, right? So R is the location on the camera. And theta is the camera angle. Okay, so now we have two-dimensional information. So this is a two-dimensional data structure, okay? And so, so this is, and this 2D structure is going to be called the sinogram. Okay, Now, a brief word about PET. Sorry, this should have been 2.1. Okay, and now 2.2, just PET. So PET, very briefly, PET is very similar, except there's no mechanical rotation of the system. So PET is a ring of detector. The patient is lying in the middle here. And then the gamma rays are coming out as pairs, right? So each time there's a decay, there's two gamma rays being emitted in opposite direction. So the idea is for each gamma ray that's recorded, we can define R and theta as if there was a gamma camera present, right? So if this is the center of rotation of the whole, so center of the system, we can define R as the distance here to the center, and then theta is just the angle of the gamma ray, right? So theta would be this angle here. So we can also sort the data coming out of PET as a function of R and theta. So we can also generate a sinogram S of R theta, okay? So whether you're doing SPECT or PET, you can create those sinograms that are a function of the two variables. And so now, maybe we're going to look more into this concept of the sinogram. Okay, so this is the sinogram. Okay, so we're only talking in 2D here. Of course, this concept extends to 3D, but just to keep things simple, and because I have to draw in 2D, I'm just going to talk about 2D. So image. So the image is a function of X and Y, and then by projecting it, by taking a measurement of the 2D distribution using a scanner, we're getting a sinogram, which is a function of R and theta, okay? So let's take a straightforward kind of example here, which is, an image here, which, so on the image, we have the center of the image is 0. This is the x-axis, this is the y-axis. And this is the center of the image, and then we have a single point source here. Okay, maybe I'm gonna use a different color here. And so this point source is located at we're going to call it x0 and then y0, right? And so if we take projections of that point source, using a gamma camera. So first, the gamma camera would be placed here. In that case, basically it's going to be, we're going to get no counts except for that location at R equal x0, right? So this is for theta equals 0. So for theta equals 0, we're getting counts nowhere, but for R equal R0. So if we now draw the sinogram, maybe side by side. So I'm going to draw the sinogram here. So sinogram, remember, is R theta. So this is going to be, let's see. Yeah, let's just do it like this. Okay. So there's going to be theta on the x-axis, and then it's going to be R on the y-axis. So the angles go from 0 here to plus 180 and minus 180. We have 90 degree here. Okay, and then here we have R equals 0. That's the center of the gamma camera. So what we said is for theta equals 0, we measured R equal x0. So I'm going to put kind of x0 here on this axis. And so what this is saying is that for this camera angle here of theta equals 0, the only place we have non-zero in the sinogram is this location here, okay? So now using a different color, I'm gonna look at placing a gamma camera on, for theta equal 90 degree. So for theta equal 90 degree, so we have R's like this. So then So basically what we're going to have is the point source is going to project on the gamma camera, and the only place where we have non-zero counts, the only place we measure in counts is for r equal y0 this time, okay? So for 90 degree, so this is the angle we're looking at, and so the only place there's non-zero count is here, and this is going to be y0, okay? And if we do that for, you know, all the angles, so rotating the camera, you know, but maybe by increment of 1 degree, we can acquire a whole, we can fill in the sinogram essentially, and fill in this whole structure with information. So here we've put zeros everywhere except there. We can fill in the rest of the sinogram, and what it's going to look like, it's going to look like a sine wave actually. So I'm trying to fit it through those points, but yeah, so it's going to look like some kind of sine wave. So the sinogram is going to be, there's going to be zero everywhere except on that black line I just drew. And so the equation for the line I drew is r equal x0 cos theta plus y0 sine theta, okay? So if the image is a single point source, like in this example, the sinogram is a sine wave, so meaning that it's zero everywhere except along the sine wave. And the equation for the sine wave is this r equal x0 cos theta plus y0 sine theta. Okay, so this is, but this is if you're on a single point source. Now, in a normal case, you don't, you know, your tracer distribution is not going to be a single point source. There's going to be activity everywhere in the image, but because it's a linear system, essentially, the sinogram is going to be a superposition of sine wave. Okay, so sinogram equal, so it's a superposition of sine function. And we'll show some examples what it looks like in practice. And it does look like some kind of sine, like multiple sine waves that have been added together. Okay, so any questions on that? So this is just sort of going over this concept of the sinogram and how the sinogram is created through the process of imaging.
When you said it's when you have multiple sources, it forms a superposition. You said it was like getting added together. Why wouldn't it be like multiple sine waves?
Well, so it's a, you know, it's basically an infinite number of sine waves, because if you think about it like an image, you can basically say an image is just the sum of kind of punctual sources, right? So essentially you could call that a pixel in your image, right? Or you can decompose any two-dimensional distribution as an infinite sum of delta functions or point sources, right? So if you had a second source, let's say here, then what would happen would be there would be a second sine wave that would be added to it. So for example, maybe like this, right?
Okay, so
I don't know, I'm just drawing it randomly, but if you had a third source, there'd be a third sine wave. And if you have an infinite number of sources, you have an infinite number of sine wave in your sinogram.
Okay, yeah, my bad. I think I was unclear as to what superposition meant. So it is multiple sine waves for each pixel.
Well, it's for each point. For each point in the image is a single sine wave, but then
okay.
Because there's, you know, if you have a distribution, you know, like this is your image maybe, right? You know, you can kind of write that as a sum of, you know, this plus this, you know, and because it's a linear system, so this is also an important part, is that those imaging systems are linear. So if you have, if you add up two different tracer distribution, the output is just the sum of the output for the individual inputs. So.
Okay, thank you. That makes sense.
Yeah, I'll just, well, thank you for the question. Yeah, feel free to stop me anytime. Okay. This is, sorry, that's an old one. Okay. All right, so now we talk about reconstruction, right? So, reconstruction is, the goal of reconstruction is solving the inverse problem. So we just talked about the Ford problem, how a distribution of tracer gives rise to a sinogram. Now, so this is what we talked about, right? So if we have a patient with a tumor and the gamma camera is right here, we've talked about the fact that just through the process of image acquisition, we're getting a sinogram, which is a superposition of sine waves. And so this is the image acquisition. This is the tracer distribution. And then the reconstruction is the inverse process. So it's basically this. So going from the sinogram here to back to the tracer distribution, because that's really what we want to know. So if you show the sinogram to a doctor, he's not going to really be able to understand what's going on with the patient, because the sinogram is kind of a very muddled version of the image. It really doesn't make sense if you look at the sinogram what's going on. So we need to go through reconstruction, which is the mathematical process, to get back to the tracer distribution here. Just give a simple example. What we mean by reconstruction is, so this is sort of an example like from the literature, but picture like you're looking at a forest, and actually there's two trees. You're trying to map the forest by taking pictures of it, right? And if you take a picture from this angle here, because the two trees are kind of in the same line of sight, the picture is going to look like essentially there's a single tree, right? It's not clear how many trees are in that line of sight. And then by taking a picture from another angle here, now the picture is going to be looking more clear, where you can see there's actually two trees here. And there's another one here. Sorry, I'm really bad at drawing trees. And so based on maybe those two or more pictures, we can sort of create a 2D mapping where the trees are in that lot, right? So that's sort of the basic idea for reconstruction, is solving a two-dimensional distribution based on one-dimensional information. But there's two ways of solving that problem, right? And so so I'm just going to give an analogy to explain why there's two different ways of solving the reconstruction problem, right? So if I give you a math problem, which is solve this equation, right? So square root of x plus 15 plus square root of x equals 15. How would you solve that problem, right? I mean, does somebody want to try, like, how would they solve? Maybe, you don't have to solve it, but maybe tell me which step you would take to solve this problem. Anyone, like, you've taken math classes, right? You probably know how to solve that. Like briefly, which steps would you take, right? So.
It doesn't seem to be that easy, so I can just plug numbers and play.
Yeah, so, okay, so it seems like kind of it's not a straightforward equation that you would just like solve. So you could try different numbers. So that's one possibility, which is we could use a kind of an iterative method. And we could just try different values of x, right? So for example, we could try x equal 10. In that case, this part on the left would be about 8.16, which is kind of less than 15. So it's x equal 10 is too small. Then we could try a bigger number, like x equal 50, for example. In that case, we would get 20.7, which is bigger than 15. So 50 is too big. So now we kind of, narrow down a value in between, right? And we could try to do that, until convergence. So eventually we're going to get closer and closer to the solution, right? So those iterative methods, we basically allow you to try different values, but there's a process by which we're getting closer to the solution by comparing the error. So here we're looking at the output and comparing to the desired value, and eventually we'll find the solution, which in that case, I think is 47. Or 49, sorry. So this is the iterative method. Is there another way we could solve it? I guess you said it was too hard to solve, but actually it's not too hard to solve, right? So we could also do, we could take this formula maybe and raise it to the square on both sides. So this would be more like an analytical solution. So analytical method, which would be, I could take, square root of x plus 15 plus square root of x. I'm going to raise it to this. I don't have those square roots, so I'm just going to raise the whole thing to the square. And then I'm going to raise the other side to the square, and so on. And so using kind of the rules of mathematics, I can eventually come out to x equal some number. And in that case, it's 49. Okay? So you can also solve it that way. So there's basically two ways of solving the problem. And so the reason I'm talking about this is for reconstruction, we can also use two different methods. So we can use analytical methods, or we can use iterative methods. And so, so today, for the remainder of the class, we're going to talk about analytical methods. And then on Monday, we'll talk about iterative methods. So this is just a kind of a brief overview. So this is, yeah, so now the next, I guess the camera looks a little blurry, but hopefully it will get better. So now, next section is about analytical methods. And let's see, where am I? Yeah, here. And so we're going to first try look at a simple way of generating images from projections called backprojection. So 4.1. So simple backprojection. And so how backprojection is a kind of another key concept of reconstruction. So the idea is that if we start with the sinogram, so this is my sinogram here, this is 0, this would be 45, and here 90, okay? And the sinogram looks something like this, for example. So first, what we do is in backprojection, there's first step would be to start with a blank image. So we're going to try to guess the image from the projection. So this is my the starting image here. So then we see that for theta equals 0, basically the only place we have counts in the sinogram is for here r equal something like a small number, right? So basically we can put a virtual camera on the image here, and then at that location r equal some value r0, so we know there's no counts anywhere in the image except from this line here, right? Because if there were counts on either here or here, there would be counts on the sinogram, but there are none, right? So because of that, we know that all the counts are focused in that spot, but we don't know exactly where the counts come from along that line, right? They could have come from here, here, here. We just don't really know. That's why, because we're looking at a single angle, so we don't really have information. So if you remember the example with the trees I showed you, we know the tree was somewhere on the line, but we don't know exactly where on the line it was. And actually, there were two trees in that case, right? So we don't even know yet if there's one source or multiple source along the line. So what backprojection does is we just kind of assume the source is present anywhere on the line, but with equal probability, right? So what we're doing is we're writing down the probability inside the image. So we're going to basically distribute the counts that we measured along for this projection equally along the line. Okay, so smearing the entire projection across the image. And then we can go to the next one. So we can look at the 45-degree data here again. So now, this is our R45. So now looking at the 45-degree, so which would be here. So now basically we're saying it's somewhere here, right? It's a negative value. So then we're gonna So this is the center of the image. We're going to say, so now we're going to smear it again, but at an angle. So now, the counts are going to be smeared here. And then we can look at the 90-degree here and put the 90-degree. And so the projection for the 90-degree would be something like this. And we're going to smear the projection like this, right? And we can continue doing that. And essentially what's going to happen is because all the projection came from, they're all consistent with each other. So as we back project more and more projections, they all going to sort of intersect in a single point. And eventually what we would get is an image of, essentially an image of this process here. So it would look at, like there will be the most counts will be in the center, but then there's some blurring. And what I mean by blurring is that, we're not really getting zero counts around that hotspot. We're getting counts everywhere in the image because each time we back projected, we put counts everywhere in the image, right? So, so that's not exactly a correct reconstruction, right? There's some blur going on. So this is using simple back projection. And so remember, so we know like if there's a single sine wave, we know that it should be a single point source in the image. So that's the correct answer. But essentially, but instead of that, we got a blurry version of the image. Okay. Because the system is linear and shift invariant, we can actually write, so this is maybe a little bit more mathematical, but we can write this blurring as...
Sorry, could you please repeat why the blurring is happening?
Why the blurring is everywhere?
Yeah, why the blurring is happening when we are doing...
Why it's happening? Yeah, so the source image, there were only counts or radioactivity in that single spot, and there was no radioactivity anywhere else, okay? But when we are back projecting the image, we because of the uncertainty, we don't know exactly where the counts are coming from. We're putting counts everywhere along the line, including outside the location of the source, right? And so the effect of that visually is a blur. It looks like a blur, and actually, so that's what I was going to talk about. It's actually it is something that can be modeled as a kind of the convolution with a blurring kernel. So you might think, what if you multiplied instead of add, right? So what if you multiplied? But if you did multiply, it would work okay for like a single point source, but it wouldn't really work if you had more than one point source in the field. But anyway, so this blur, actually, I don't know if, let's see if I can perhaps show, yeah, I can try to show you a more visual version of it. Yeah, so if I could share my screen again. So as you see here, so this is sort of the same thing but done using a computer. So I have a radionuclide distribution here. That's the sinogram that's computed from that radionuclide distribution. And then as we back project the lines one by one, the effect of it is there's a halo. I mean, I say a blur, but it's basically like a halo that's around the source. But it is essentially, it is a blurring. It's a loss of high frequency information. So what's going on is the low frequency are being emphasized to the detriment of low frequency of high frequencies. So high frequencies are being lost compared to low frequencies. Okay. So just going back, so we can model this. So this is we're going to call this image f of b of x, y. And we're going to call this one f of x, y, which is the true image originally. And so because it's a linear shift invariant system, so this type of system is modeled by convolution. So when I say system, I mean the process of going from a 2D distribution of the tracer, creating a sinogram, back projecting the sinogram like this. So basically this whole process is linear shift invariant. So therefore it can be represented by a convolution. So the whole pipeline is summarized by this convolution. And I guess this is something you kind of have to accept. I can't really demonstrate why, because it's a whole class in itself. But so this is the blurred back projection image, right? Which is if I was just looking at in 1D, that's what it would look like. And it's equal to the original image that was not blurred. And then, so this symbol here means convolution, right? So convolution with a blurring kernel KB of X, Y, okay? And we don't know what the blurring kernel looks like so far, but we'll kind of show what it looks like. So the idea is if we could figure out what the blurring kernel looks like, we can actually correct for the blurring and ideally get back to the original image that doesn't have the blur, right? So that's the type of reconstruction we need to do to get the correct image, is to remove that blurring. And that's where I'm going to introduce another type of operation called filtered back projection. Okay, so filtered back projection. And so the goal of filtered back projection is to remove the blur, so generate an image that doesn't have the blur. And how we're going to do that is by looking at the images in the frequency domain. So that's why I had the refresher on Fourier transform and frequency domain. And the algorithm that's going to be used to understand the blurring is called the Fourier slice theorem. Okay. And just a few words about this Fourier slice theorem. So actually it was kind of invented at Stanford. So I mentioned that. It was in the 50s by a professor named Bracewell. And Bracewell worked on microwave, radar, and things like that, and basically came up with this concept of Fourier slice theorem, and then realized it was applicable to imaging. And I think this was a very consequential theorem for medical imaging, because it shows that we can essentially reconstruct the images perfectly just by acquiring projections of the images. As long as we have enough projections, we can reconstruct that image perfectly. And so so I'm not going to really go through the math, because that's not the point of the class. The class is supposed to be kind of an introduction and trying to understand things more qualitatively. But so I will just go through that visually, essentially. So we start with a two-dimensional tracer distribution, like we've done in other examples. So this is called f of xy. This is the tracer, how it's distributed in 2D. So as usual, we have x and y, okay? And then I'm going to show you an example here. So what happens if we take a projection of this tracer distribution like this, right? So what happened is basically we're getting a projection of it like this. But the key thing to understand is that this projection contains all the information we need in terms of horizontal frequencies. Sorry, I just have somebody knocking on. Okay, sorry for the introduction, for the interruption. So what I meant, so this projection here contains all the information I need in terms of horizontal frequency, because essentially it's taken orthogonal to the orthogonal to the horizontal axis. So all the horizontal information has been preserved, right? But it's the averaging that takes place. So when we look at those projections, basically we're averaging the distribution along the y-axis, and so all the y information has been averaged out and kind of been lost, right? So we lose all the information about the y frequencies, the vertical frequencies, but we keep all the information about the horizontal frequencies, right? And so the intuition is that when we take a projection in the frequency domains, if we look at in terms of frequency, we actually are measuring, so this is ky and this is kx. Sorry, I guess I'm need to move a little bit. Let me just, can you? Yeah, I think I can put it here. Okay. So in terms of frequency information here, what we're getting is really, we're measuring the frequency content of the image, but along this line, okay? So we're measuring all the horizontal frequencies because they're preserved, but we're losing the vertical frequencies, and all we're measuring is the DC term for the vertical frequency. So by averaging out the image, we're measuring the average signal, which is the DC term, right? The zero frequency essentially is the average of the signal. So now going back up here, so if we look at instead of looking just at the one angle that's, theta equals 0, we can look at an arbitrary angle theta. And if we acquire a projection at this angle theta, we can basically represent this like this. So this would be theta, this would be R, and then this is our, if you remember, this is our sinogram S of R theta. And so now we're looking at projection this way. Okay. So this would be the projection for this angle R and theta. And the intuition we had that basically the projection preserved the frequency information along a single line in the spectrum holds true for any angle, right? And so actually, what the theorem says is I can take a 1D Fourier transform of this projection. So just taking this 1D Fourier signal and take a Fourier transform of it. So this is a 1D Fourier transform along the variable R. And so now I can go in the frequency domain. So now we have the variable here is, sorry, KR. This is still kind of theta. So that, taking the Fourier transform doesn't change anything but the angle, just change because we're taking the Fourier transform along R. And so now this is the spectrum of the image. Sorry, the spectrum of the one-dimensional projection that's shown here. Okay, and this would be the kind of the DC term, the zero frequency, and these are the low frequencies and the high frequencies. What we can also do is take that 2D distribution of the tracer and take a 2D Fourier transform. So a 2D Fourier transform. And then we can sample it at an angle theta. So first step would be to take the 2D Fourier transform here. So again, this will be Kx, Ky. So we moved into the frequency domain, and this would be our spectrum information here. And then I said sample at an angle theta. That means I will just look at the 2D Fourier transform along that line. Okay, and I can plot that. So if this is, sorry, this is Ky and this axis is Kx. So I can plot the spectrum. So I go from a two-dimensional spectrum here, and I take just to extract a one-dimensional profile from the spectrum, and I plot it here. Okay, and so the point that the theorem makes is basically that those two things are equal. So okay, so this spectrum here and this spectrum here, if you compare them, they're exactly the same. Okay. And so, okay, so I don't know, it may seem obvious to some of you and it seems intuitive, but I guess it was a kind of a important discovery, because what it means is I can start from an image, acquire a projection, start from a tracer distribution, acquire a projection of it, take a Fourier transform of that projection, and then repeat that for multiple angles. And by doing so, I can sample the full spectrum of the tracer distribution. So if I were to change the angle, I'll basically get information about the spectrum along a different line, okay? So each time we take a different projection at a different angle, we're sampling the two-dimensional spectrum of the tracer distribution at a different angle. And so by collecting information for all the possible angles, we can build the full spectrum of our tracer distribution. And once we have the full spectrum, there's actually an inverse Fourier transform that allows us to go from the frequency domain back to the spatial domain, and therefore we can obtain a full accurate reconstruction of the image. Okay. The other thing is, because the spectrum is symmetrical, we really only need 180-degree coverage of the image, sorry, of the distribution to get a full reconstruction, right? So, full reconstruction for 180-degree coverage. So that's one of the conclusion of the. So this is a kind of a key theorem for tomographic reconstruction. Any question about this? Yeah. Okay. Good. So now going back to back projection, right? So yeah, I think we'll try to finish that and then see. Yeah. So I'll cover the simple back projection and we'll finish on Monday. So if we start from so when we were doing with back projection, if you remember, let's see if I can. Yeah. So if I can put it back, so we had a when we did back projection, we had a sinogram, and so what's going on is we were basically taking a projection here, and then we were back projecting the projection into the image domain. So if we look at what's happening in the frequency domain when we do that, so this is a x, y, so this is the image domain. In the frequency domain, when we do simple back projection, this is what happens, right? So now this is kx, ky. So by back projecting, we are filling in the spectrum. So for this first one, by back projecting, we're basically filling in this part of the spectrum. So it's kind of perpendicular to the direction, because the projection is taken along this axis. That means we're collecting information in the perpendicular direction here. So that would be the first. Then when we back project the second projection view, so this would be another theta value, for example. Then it's filling in this part of the spectrum. It's adding up actually, right? So because we're adding up, actually we're adding up. So this point, for example, gets added twice. And then if we're doing a third projection view being back projected here, then in the frequency domain, it adds up like this. And so if you can picture that being done for many different projection view, in the frequency domain, what happens is this is we're filling in the spectrum, but each time we're filling in spectrum, it's not done kind of in it's not being done in a uniform way, right? And especially the low frequencies get sampled over and over repeatedly, and each time it's each time we're sampling a new projection view, we're sampling the DC term and adding it up. Whereas in terms of the high frequency, they only get sampled maybe once at best, right? Or if sometimes not even get sampled. And so this creates an imbalance between the low frequencies that get sampled many times and the high frequencies that get barely sampled by the process. Okay. And so there's an oversampling of low frequencies with respect to high frequencies. Okay, so that's what leads to the blur, because remember, low frequencies are kind of the coarse details of the image, whereas the high frequencies are the sharp, kind of fine details of the image. And by doing this process of back projection, we overemphasizing the low frequency details of the image. So the image, which was initially quite sharp, becomes kind of blurry. It's the low frequencies are dominating the content of the reconstructed image as opposed to high frequencies. And so the solution is actually to this problem is kind of a relatively straightforward one. So first thing is to notice that the oversampling factor is actually, it can be calculated. So I'm not going to do it, but I'll just give you the answer right away. So the oversampling factor is 1 over KR. Okay, so KR here is defined as KX squared plus KY squared root. So KR is, the idea of KR. So if you are in this axis here, KX and KY, KR is just the distance to the center of the frequency spectrum. So this would be KR here. Okay, so if this is KX, this is KY, KR is the diagonal, right? It's and so the oversampling factor is KR. So here the center KR is 0. And then at the edge of the field, KR takes larger values, right? The largest, so essentially it's like you have those concentric rings, right? So KR is constant along those concentric rings in this frequency spectrum. But this is the oversampling factor. And so to solve the problem, we need to basically multiply by the inverse of 1 over KR, which is just KR. And so if we go back to that equation we had before, let's see, where is it? So yeah, so here, if you remember this equation here we talked about, so now we can actually say that, so we had FB of X, Y equal F of X, Y was convolved with some blurring kernel that was unknown. If we go in the frequency domain to the Fourier transform, we can take the Fourier transform of the reconstructed image, which is FB of KX, KY, and then the Fourier transform of the original tracer distribution, which is F of, so I use, sorry, KX, KY, I use a capital letter to say it's a Fourier transform. And then one notable property of Fourier transform is that when you take the Fourier transform of a convolution, it becomes a simple product. So now it's just a multiply. Okay. And then, so we've just said that the oversampling factor is 1 over KR. Okay. So that's the oversampling factor. And so to solve the problem, so to remove blurring, we basically multiply by, we're going to multiply by KR. Okay. So the idea is, so to remove the blurring, what we could do is we can take projections, put them into the frequency domain, multiply them by KR, and then bring them back into the spatial domain, and then we can do a simple back projection. So I'll write that down, procedure. So this is the procedure for filter back projection. So first, well, we have to acquire the projection from the subject. So there's an angle. Then we're going to do 1D Fourier transform of the projection. Oh, what did I do? That's a 2. Then number 3 would be to apply this KR, and this actually is called the ramp filter. So it has a name. So we're going to apply. Oh, I guess it's. So apply ramp filter. So this term of ramp filter, and why we call it ramp filter is because if you actually plot what the function looks like, so this is KR, it actually looks like this. Okay. So it looks like a ramp going, kind of going up, like a straight ramp. And the next step would be, so 4 would be take inverse Fourier transform. So we take the inverse of the Fourier transform. And then 5, we can back project all angles. Okay. So just wanted to show kind of more visual example for this. So this is from, I guess, one of the textbooks that's used in other classes, but this is what it looks like. So when we're doing, so the idea is when we're taking the Fourier transform and multiplying by the ramp filter, actually what happens is it creates those negative values around the peak, right? And so when the filtered back projection when the filtered projection is back projected into the image, there's those negative wings around the peak that essentially will cancel out the blurring that we saw initially. And so when all the multiple views are being added up, all the counts that were recorded here kind of cancel out with those negative wings around. And the negative wings are really designed to basically give you the desired outcome. So that's the procedure. Let's see. Yeah. So actually, yeah, I think I can actually finish the analytical reconstruction before the time. Yeah. So there's one last thing I wanted to discuss on this topic, and it's the impact on noise, right? So noise is always, it's an important problem in any type of engineering or imaging application, because noise is present everywhere, especially when there's few counts that are being recorded by the scanners. There's going to be noise in the images, right? And
again, can you use a fresh piece of paper? I think we can see.
Yeah, I was actually thinking, but yeah.
It's kind of a waste of paper, but anyway.
No. I think we can afford. Yeah, that's right. I was actually noticing that. Yeah, good point, Craig. So we're going to talk about the impact on noise. If you go to the lecture notes, there's actually kind of more details about noise and the type of noise that's present in PET images. The dominant type of noise in PET images and SPECT images is called Poisson noise. And the lecture notes kind of go in more details. You can read if you're interested. This is not going to be on the homework or anything, but it's there if you want to kind of go deeper on that topic. But so this is the sort of a high level view of noise. So noise in the image, if you have an image that contains noise has a frequency spectrum as well. So if you were to just acquire like I don't know, using your camera, like a picture camera, you can take a picture of something that's uniform color, right? A white sheet of paper, for example, right? So the sheet of paper is perfectly white, but then if you look at the image, there's a little bit of noise, like the pixel value will not be exactly the same for all the image. So that's due to noise. That's because either the electronics, or it can be due to physics. There's different reasons. And you could take a Fourier transform of an image of the noise and look at the frequency component of the noise. And most type of noise are called so-called white noise. So white noise, so not white like the color white. And this is meaning that essentially there's no correlation between the noise in the different pixels of the image. So the noise is truly random, meaning that it's essentially a random quantity that's added to each pixel. And there's no correlation or relation between the noise in one pixel and the noise of any other pixel in the image. And when you have white noise, which is this random type of noise, the frequency spectrum of the noise, so if I plot as a function of KR here, so this is taking a 2D projection, sorry, a 2D spectrum of an image, the noise is going to be present in all the frequency bands of the spectrum. Okay, so the noise is, you have low frequency noise, medium frequency noise, and high frequency noise. The signal, however, because the signal is coming out of a camera which has limited spatial resolution, so that means the camera can only capture details of the image or details of the distribution up to a certain level of detail, right? It's so it can capture the low frequencies, but it's gonna struggle to capture the high frequencies. And this is also something that's mentioned in the lecture notes. But the signal is gonna be, so it's gonna contain, a certain amount of low frequency signal, but then because of limited spatial resolution of the camera, there's not going to be any useful high frequency information in the signal, right? So this would be the signal here. Okay, and so, if you talk about signal to noise ratio, we can see that in terms of low frequency, we have a abundant signal compared to the noise, but then in the high frequency, the information of the image is dominated by the noise. So there's more noise than useful signal. So what happens when we multiply by the ramp filter? So remember that we said that we're going to be multiplying each projection by a ramp filter. So then what happens is that, so remember the ramp filter is a ramp, so it's just something like this. When we multiply those two things together, so it will give us this here. Yeah, so what it will give us is, the noise, basically we're multiplying something that's flat with the ramp. So it's uniform versus ramp, it's gonna give us a ramp. So this is gonna be the noise. And then for the signal, we're trying to multiply this black curve here with the red curve. And in the low frequency, it's actually gonna suppress the signal. And then in the high frequency, it's gonna go like this, right? So here, because the signal goes down to 0, we're going down to 0. But then here, because of the ramp filter, we're actually suppressing the signal here, and it's going down to 0 as well. And so there's this point here, basically, that this frequency where on this side, noise is smaller than signal. And on the other side, the noise is larger than the signal. So so this is actually what's going. This is referred to as noise amplification. I guess I'm getting. So this is referred to as noise amplification. So, so we had mentioned that by backprojecting the data, we're emphasizing low frequencies compared to high frequencies, and by multiplying by the ramp filter, we're trying to rebalance the different frequencies, and we do that by emphasizing the high frequencies. But the problem is by emphasizing the high frequencies, we emphasize the component of the noise which is in the high frequency, right? So we're emphasizing this section of the noise, and if we were to do nothing, the images will be very noisy and they wouldn't be very useful. And so that's why we need to implement another approach to get usable images, which is to incorporate a gradual roll-off in the ramp filter. So if this is the ramp filter here, instead of using a pure ramp that's emphasizing the high frequency content in the noise, we can use something that has a roll-off. So for example, this would be an example of ramp we could use. And this is called the Ham filter. Sorry, not Ham, Han filter. And this will reject some of the high frequency noise because we're forcing the ramp to go down to 0. Therefore, the noise that's present in the high frequency part of the spectrum will not get emphasized. There's other variation of this, of course. There's another one called, that's more like this, called Shep-Logan. So which, maybe like reaches more like a plateau instead of going all the way down back to 0. And so on. So what this is referred to globally is, so it's noise rejection, but it's called also known as low pass filtering. Okay. All right, so I mean, that's basically so this is the filter back projection. And so just to recapitulate, so filter back projection, the idea requires projections from different angles. We have to filter them so that we can apply the ramp filter or apply a suitable filter that has noise rejection, such as a Ham filter. And once the projection have been filtered, they can be back projected into the image one by one. So if a ramp filter is used, and there's no noise, that will give a perfect reconstruction. If there's noise, that will give a very noisy version of the original image, but it will contain all the frequencies that were originally present. And if one of those filters is used, the hand filter or the Chaplogin filter, it's going to get a version of the image that has less noise, but it's going to look a little bit blurry because we are losing a little bit of the high frequency content of the distribution, right? So because of the roll-off, some of the signal is going to get attenuated. So the image is going to look a little bit more blurry, but the advantage is that it will have less noise, okay? And so basically next lecture, I will start just by showing actually images and examples of this. So I think today we don't have time, but on Monday, I'll definitely show you some examples of filter back projection for different type of objects. And we'll see like the sinogram, and we'll look at reconstruction using different methods. Let's see, any questions for the class? I can definitely stick around for a few more minutes if you want to stay and ask specific questions about the lecture.
Hi, yeah, I did have a question about the filtered back projection, or sorry, the ramp filter.
Okay.
And so you were saying that part of the benefit is that you can compensate for the too many low frequencies, and so you're trying to de-emphasize them to improve the to decrease the blurring. Mm-hmm. But that doesn't really have anything to do with the actual resolution, does it? You couldn't do a sharper ramp that goes like parabolic to make it even more high frequency?
Well, so the ramp filter is the ideal filter because it gives you exactly the right balance of frequencies that you had originally in your image. Okay.
I see. So it's like more of a compensation.
So it's really, yeah. So mathematically, you can show it if you have no noise. If you run an image through a scanner and then apply the filter back projection with the ramp filter, you get exactly the same image, and you can test them, by writing code and doing different tests. If you did a parabolic, like you suggest, a parabolic ramp filter, you would affect the frequency content in your original image, and you would emphasize the high frequency detail of your image, and you can do that, and your image will just look kind of artificially sharper, right? But when the image is too sharp, you start getting artifacts like you may get sort of oscillations around edges, for example, because it's adding all those high frequencies that were not really present originally. But you're right, it will give kind of the visual impression of being kind of, the edges will be sharper, and there's going to be, everything is going to look sharper, but it's not real, right? It wouldn't be like, it's not like you're going to see things that are artifacts that they're not really present in the original distribution. So the goal of reconstruction, we're trying to get back to the actual distribution of the tracer, and we're not trying to like improve it, right? We're just trying to show it the way it is. Your camera, the camera itself, so I didn't talk too much about it, but the camera will attenuate some of the high frequencies, like because of the collimators, because of the detectors. And you could try to, you could think about, like you say, adding a parabolic filter to try to remove the effect of the camera on the distribution. So that's something else, right? But that's right. You could try to do that also, right? Because your camera is losing resolution, it's losing high frequency information, and so you could try to compensate for that. But again, the issue is the noise. If you don't have enough signal to noise ratio, as shown here, this is going to have a detrimental effect on the image by really increasing the noise, because noise is present in all the frequency bands, and high frequency noise can be, especially damaging in terms of obscuring the details of the image.
Yeah, can I say something again? So we're very count starved, and molecular imaging generally, especially a PET and SPECT radionuclide methods, you're really count starved. So you always have a lot of high statistical noise, so low statistical quality data. And so in addition to sharp edges being enhanced by enhancing high spatial frequencies, the very sharp changes in counts that you see as a result of low statistics would also get enhanced if you amplify the high frequency. So for that reason, you'll never see them really reconstruct using a ramp filter unless you have just a huge number of counts for some reason, or maybe you're reconstructing a point source and error or something like that, usually you won't ever use a ramp. You'll always turn it over, like the Shep, Logan, and Ham that Gam's showing you, to actually mitigate noise with the knowledge that you're going to slightly blur out sharp edges that are real signal. So it's just because the noise actually ends up being a bigger problem.
I see. Thanks. That makes a lot of sense.
Well, thank you for the question. Okay, well,